Good afternoon. I'd like to welcome those of you who've joined us today. My name is John de Villiers. I'm currently a master's student at Nelson Mandela University. This paper forms part of the results of my master's project. I co-wrote the paper with my supervisors, Professor Andre Karlitz and Professor Jean Schrelang. The following is an overview of the outline of this presentation. I describe the background context surrounding the motivation for the paper. The proposed approach is fleshed out and the methodology is provided. The results of the investigation are illustrated and discussed as part of the conclusion. The Bootstrapped Neurosimulator, or BNS algorithm, is a bidirectional extension of the simulated neural network method developed as part of the research output of the Computational Intelligence Robotics Lab at Nelson Mandela University. The goal of the BNS algorithm is to evolve satisfactory policies and train a simulated neural network or ensemble of simulated neural networks for a specific task on real-world robots in a bidirectional concurrent process. A typical simulator used by BNS takes as input the previous action and the current action, and outputs the changing position of the robot. The simulator is trained using backpropagation based on historic data collected in earlier stages. Most research on BNS has been conducted on open-loop control problems. Policies are thus based on information or feedback from the environment or prior actions made by the policy. Open-loop control systems are typically less complex than the closed-loop counterparts, but cannot correct for errors nor engage in typical machine learning. However, the BNS algorithm has been successfully applied to a single closed-loop control robot for a simple light-following problem, whilst exhibiting damage recovery behavior. Closed-loop control tasks tend to be significantly more complicated and interesting problems than open-loop control problems. A typical means of representing closed-loop control problems is to model them as Markov decision process problems or partially observable Markov decision processes. These types of processes will be referred to as Markovian processes. Markovian processes are the typical means of representing reinforcement learning problems. In a Markovian process, a learner agent is situated within an environment and is tasked with completing some goal. How well the learner agent performs this goal at a given time is quantified by the reward signal. For closed-loop control problems, an agent perceives the state observation of itself within the environment, and the action the learner agent takes is partially dependent on the current state or reward within the environment. Whilst, for open-loop control problems, the learner agent does not use state or reward information to inform the actions taken. A distinction exists between a state and observation, as a state provides perfect information about the learner agent within the environment, whilst an observation provides imperfect information. This distinction has led to the use of Markov decision processes or partially observable Markov decision processes, respectively. A typical means of representing closed-loop control problems is to model them as Markov decision process problems or partially observable Markov decision processes. The following describes the BNS approach as part of the evolutionary robotics process. Step 1. A simulated neural network and a population of policies are randomly initialized. Policies are selected from the current population of policies and evaluated on the real-world agent. Behavioral data from these evaluations is stored in a training data buffer. Step 3. The stored training data periodically integrates into the simulated neural network training. This increases the accuracy of the simulated neural network predictions. Step 4. The training simulated neural networks are periodically copied and used to replace the simulators used in the evolutionary process. The population of policies are evolved using the newly updated simulators to estimate policy fitness. Step 5. The process repeats from Step 2 or until the appropriate termination criteria are fulfilled. Bootstrapped Neurosimulator has only been applied to a limited number of mostly open-loop control problems and a single closed-loop control problem on a small set of robotic hardware or navigation type scenarios. A bootstrapped neurosimulator-like approach has not been empirically demonstrated to be applicable to Markov decision process problems, such as those used in reinforcement learning, a domain tasked with policy optimization, similarly to Bootstrapped Neurosimulator. Existing research indicates that Bootstrapped Neurosimulator has only been compared to different instantiations of itself and other simulator neural network methods. This paper presents the results that indicate that Bootstrapped Neuro-Evolution, which is based on some of the principles underlying Bootstrapped Neurosimulation, addresses these potential shortcomings. Bootstrapped Neuro-Evolution provides tangible improvements to sample complexity of its constituent evolutionary algorithms. Step 1. Randomly initialize a population of policies and the simulator neural network. Step 2. Evaluate the fitness of the generated policies whilst only using the real problem environment's fitness function. During this evaluation, gather simulator training data in the form dictated by the input and output of Figure 4 and pass this training data to the simulator neural network dataset. Step 3. Use the simulator dataset to train the simulator. Once sufficiently trained, pass the simulator to the simulator fitness function evaluator. Step 4. Pass the fitness values back to the population of policies. Step 5. Evolve the population of policies. Step 6. Evaluate the fitness of a policy. Pass it to the fitness evaluation function. The fitness evaluation function decomposes the fitness into a real problem environment's fitness function and simulated fitness function. Step 7. Evaluate the fitness of the policy in the real problem environment whilst probabilistically gathering simulated trained data as in Step 2. Simultaneously evaluate the fitness of the policy using the simulator fitness function. Periodically use the simulator dataset to train the simulator and replace the simulator used by the simulator fitness function, similarly to Step 3. Compose the real fitness value with the simulated fitness value following the fitness evaluation function used and pass the fitness of the policy back to the policy optimization population. Step 8. Return to Step 5 or until the terminating criteria are met. The simulator in the Bootstrapped Neuro-Evolution approach takes as input an observation and action and passes these values through the neural network to predict an observation and the reward for the subsequent time step. BNE's policy neural network takes as input an observation for the current time step and passes this through the neural network and uses this to output an action to take for the subsequent time step. In this paper, we investigate the performance of Bootstrapped Neuro-Evolution on 3 different problem environments of increasing complexity and 2 different evolutionary algorithms with different configurations for the simulator neural networks and policy neural networks. Investigation 1 made use of a simple reinforcement learning environment called CartPole. CartPole is a 2D environment where the goal is to balance a pendulum on a cart that can move freely from left to right. For every time step that the pendulum hasn't fallen over, the environment returns a reward signal of 1. If the pendulum falls over, however, the environment terminates and returns a reward signal of 0. Investigation 2 makes use of the lunar lander environment, which is also a 2D environment. In this environment, the goal is to land within a predefined goal region whilst minimizing fuel consumption. The policy can fire none or one of 3 engines at any given time. Investigation 3 uses a 3D physics simulation of Ghost Robotics' Minotaur, a quadruped robot. The goal of this environment is to move as fast as possible whilst minimizing the energy expenditure of the robot. This is by far the most complicated environment used in this paper. The simulator architectures used in these investigations were tuned using Bayesian optimization with hyperband. Trajectories were randomly sampled and split to form the relevant training, test, and validation sets. The best found configurations were used to select the simulator neural network architectures used in each investigation. This process was conducted prior to each investigation. The policy neural network architectures were not directly tuned and are the default settings. In the first and second investigation, we made use of a mu, lambda evolution strategy. For each successive generation, mu individuals are deterministically selected from the lambda child population and used to replace the parent population mu. Initial tests that used the evolution strategy from investigation 1 and 2 were not successful for the problem environment used in the third investigation, so an estimation of distribution type evolution strategy was selected instead. This evolution strategy is similar in concept to the one that was successfully used by OpenAI in their paper that helped to restart general interest in using Neuro-Evolution for policy optimization. Evolution strategies are a class of evolutionary algorithms where the mutation operator samples a probability density function for a random vector. This random vector is used to represent or generate a candidate solution. This mutation operator is typically self-adaptive and is updated according to previously sampled candidate solutions and their fitness or relative fitness values. From a design perspective, evolution strategies are especially interesting as they view the inspiration, natural evolution, as a self-adaptive process. Thus, evolution strategies tend to be more robust to hyperparameter choice, and do not require excessive hyperparameter optimization. The Ackley function is a commonly used test function for optimization algorithms. In this two-dimensional variation of the Ackley function, it is characterized by a relatively flat outer region that transitions into rolling hill-like features before culminating in a steep cliff at the coordinates -5, -5. The trick to this optimization problem is that there are many steep local optima that a search algorithm might get trapped in. As can be observed in this example, the search algorithm disperses the population over a relatively large area and continually expands the search along the area of greatest expected reward. The mutation parameters are updated periodically, and once a new optimum is found, subsequent generations may converge on the new optimum. A variation of this evolution strategy was used for the third investigation. Each investigation was conducted over 20 trials per algorithm. The fitness of every individual from the evolution algorithm was recorded. For every investigation, the median best individual across every trial for every generation for each algorithm is presented. The more interesting results can be observed by the figures that represent the median fitness bound by the 10th and 90th percentiles of each algorithm across every trial per generation, and by the mean fitness bound by a single standard deviation. Generations that perform better are identifiable by vertical green bars where the null hypothesis of the Wilcoxon-Mann-Whitney test was rejected for the given test statistic at the indicated alpha level. In investigation 1, we can clearly see that the mean and median fitness curves increase at a faster rate for bootstrapped Neuro-Evolution, and that this is captured by the lower and upper bounds being consistently higher than the evolutionary algorithms. Both evolution's learning curves are stereotypical exponential rise to limit curves. Thus, rapid progress is made which gradually tapers off as the limit of the environment is reached. Bootstrapped Neuro-Evolution performed 59 trials, whilst the evolutionary algorithm performed 61 trials. In the second investigation, a clearer distinction can be observed between Bootstrapped Neuro-Evolution and the evolutionary algorithm. Like the prior investigation, both algorithms exhibited an exponential rise to a limit. However, Bootstrapped Neuro-Evolution exhibits two separate exponential rise to a limit curves, unlike the evolutionary algorithm. Bootstrapped Neuro-Evolution performed 54 trials, whilst the evolutionary algorithm performed 50 trials. Investigation 3 presents the idealized general form of a learning curve, the S-curve. Small, incremental fitness improvements are made that are subsequently followed by large improvements before the improvements taper off and the limit set by the environment is reached. A large, more noticeable distinction may exist if more training data was gathered to train the simulator, or if the optimization algorithm was presented as a true multi-objective optimization problem. The third investigation made use of fewer trials, primarily as it required significantly longer periods of time to conduct those experiments. Bootstrapped Neuro-Evolution ran for 26 trials, and the evolutionary algorithm ran for 22 trials. This paper presents the novel Bootstrapped Neuro-Evolution algorithm that has been demonstrated to be performed as a policy optimization algorithm and produces a simulator trained in a bidirectional approach. Bootstrapped Neuro-Evolution was evaluated on partially observable Markov decision process problems typically used in reinforcement learning. Bootstrapped Neuro-Evolution has been shown to be a viable algorithm that doesn't require significant hyperparameter optimization that can be added to the repertoire of evolutionary algorithm practitioners. I would like to acknowledge the contributions made by my co-authors and supervisors, Professor Andre Kollitz and Professor Sean Schreller, as well as the use of the CHPC resources. Lastly, I'm available for 5 minutes of questions. Thank you very much.